Salut și bine v-am regăsit la podcastul Tehnocultura. Suntem la episodul 124, denumit Ai Bolt, Ai AI. Gazdele tale preferate, Vlad, Bănică și Manuel Cheța te salută. Hello, Vlad!
Salutare!
Bine te-am regăsit. Uite că de data asta o să avem un episod special, o să avem câțiva invitați, nu câțiva, ci 2 invitați, care lucrează în domeniul AI și care lucrează chiar la firma Bolt. Toată lumea, cred că din România, știe ce este firma Bolt, unde se pot duce oamenii și folosi aplicația respectivă să meargă din loc în loc cu mașina. Dar ne pot da mai multe detalii cei de la Bolt, care lucrează foarte bine pe AI. Și așa că subiectul principal de astăzi vor fi discuții serioase despre AI cu Andrei Ilie și Martin Lumiste de la Bolt Europa. Și dar fiindcă Martin nu vorbește limba română, este din Estonia, podcastul de față este înregistrat în limba engleză. Și un cuvânt de introducere înainte de a începe vorbirea noastră în limba engleză, episodul în limba engleză. Andrei și Martin au ocupat recent locul al doilea la competiția NEUR IPS, Traffic Forecast, în 2022. Eveniment la care concurează tot felul de institute de cercetare și, bineînțeles, provocarea din ediția respectivă a fost de a utiliza informațiile de tip sparse traffic, pentru a prezice nivelul traficului pentru un oraș întreg cu 15 minute în avans, deci un fel de Minority Report, ceva de genul ăsta. Bineînțeles, Andrei și Martin au creat un algoritm foarte simpatic, foarte rapid, care necesită puține resurse computaționale. Chiar am citit, puteai să lucrezi pe algoritmul respectiv pe laptop. Soluția lor utilizează o anumită abordare numită Gradient Boosted Trees și, bineînțeles, poate fi aplicată cu ușurință practică și mult mai ecologică în alte soluții. Chiar avem un link în show notes care duce către clubitc.ro, unde se povestește puțin mai mult despre ceea ce au făcut Andrei și Martin. Și așa că vom trece acum la vorbit în limba engleză. Cel mai probabil o bună parte dintre ascultătorii noștri știu limba engleză, dar o să fie pentru prima oară când ne vor auzi vorbind în limba engleză. So, we're going to start speaking in English now, and we're going to make sure that Martin and Andrei are able to understand ourselves, and we can take the discussion from here. So we're really glad to have you in our episode. Welcome, Martin. Welcome, Andrei. Can you guys speak a bit about your role at Bolt Europe? And we're going to start with Martin. Just a couple of words from you. Like, what's your role at Bolt, and what's your involvement in terms of AI?
Yes, salute. Sorry that you have to do it in English because of me, but so at Bolt I'm involved in a role called technically as group tech lead of the data science team, which is currently a team of 35 people, I think, who are mostly so data science can mean different things, of course, in the industry. In our company at Bolt, it means essentially people who are training machine learning models and trying to apply them either in the product or in some internal processes, basically trying to optimize something at Bolt. I've worked at Bolt now for over 4 years, so that means I've been training many different machine learning models for many different use cases, but these days as group tech lead, I'm mostly just trying to support the different teams with, technical know-how, maybe trying to direct them in like more productive directions sometimes. Most lately actually been working on some interesting large language model use cases.
Yeah, we're going to get to the point of language models and training models and whatnot later on, but let's see what Andrei has to say.
Hello, and first of all, thanks for having us and for having this special edition in English with Martin as well, who apparently knows a little bit Romanian. I'm Andrei. I've been working at Bolt for over 3 years now. I'm currently working as an engineering manager for the data science team. I'm managing a group of 3 data science teams. One is working on the maps-related aspects, such as predicting ETAs of cars moving in the city. Another is called rentals. This is the data science team dealing with the machine learning problems related to scooters. We've also got like the scooters business at Bolt. And the third one is the delivery data science team. This is pretty much everything that uses machine learning from the Bolt Food application. And as I was saying, I started at Bolt more than 3 years ago. Actually, it's been 3 years, like three days ago. And I initially started working as a data scientist, working mostly on the ETAs aspect. So this was sort of my first topic in which I eventually got specialized. Working on the machine learning models that forecast those ETAs, which some people might hate, some might love, but we're continuously working on them. It's a hot research topic at Bolt.
Yeah, awesome stuff. I'm going to ask 1 or 2 questions, and then I'm going to ask Vlad to ask you some other questions. So quite often we're going to hear that people are speaking about AI, and then they jump to machine learning, and then AI back again. So are these interchangeable? What do these two mean? Because most of the time we speak about AI in our podcast, we speak about ChatGPT and all of the other stuff. But what's the difference between these two?
All right. So, very, very good question. Traditionally, if we go back in history, AI or artificial intelligence has been a separate, much wider research domain. But I'd say today it has converged to the state where essentially any cool AI model that you see, it's built based on machine learning. So I'd say the common usage of the term is that any system that kind of reminds you of what a human could be capable of doing. So all the vision models, the text models, that's usually referred to as AI. While if you have like more traditional use cases, like for example, time series forecasting, then that's today called as machine learning. But in the back end, if we talk about ChatGPT, then it's actually also machine learning that's powering that model. So it's the same methodology.
Okay, so then my next question would be a more difficult one. So how can a machine learn? So I've read a book, which is really nice book, a nice book called Life 3.0, written by Max Tegmark. I guess you heard of him. So basically, he was explaining the AI conundrum we're living in, and basically that actually, when you're talking about AI systems, machine learning, whatnot, machines can learn, machines can be intelligent. How can this be possible? Because I thought I would be the only one intelligent between me and the machine, but then machines can learn and they can also be intelligent. I don't like that. So why is it happening, and what does it mean?
This learning part is more about finding and exploiting statistical patterns in data, and this would be like the most basic form of it, where you've got some what we call supervised tasks, where you've got some historical data with some outcomes. The classic example would be prices of apartments, and you'd get some features like how old the apartment is, how many rooms it has, what surface it has in square meters, and so on. And you'd have to forecast a price, like what price would a given apartment that you haven't seen before have, and then classic algorithms work by fitting algorithms as simple as linear regressions on top of this data, gradient boosted trees, which we would speak about later on. So there's a big suite of algorithms that can just learn from available data. They can find statistical patterns, and they're good at forecasting previously unseen data. This sort of work has been done in the past even by hand before being able to implement such algorithms. It was statistician work. Later on, statisticians would use computers and algorithms in order to aid their work, such that they wouldn't have to go through this manually. And later on, there would be a broader and broader class of potential algorithms that can help you with this purpose of learning from data, of uncovering statistical patterns that you would then use to forecast stuff for unseen data. So it is some sort of learning. It is some sort of learning, and this is just the simplest. I would say this is just the simplest take. Then you can discuss about more complex scenarios, such as the one of reinforcement learning, where you've got agents interacting with the environment, and then you can argue that those are actually learning more because they're subject to doing some actions, observing some feedback from the environment, and then deciding how to act optimally. That's a bit more complex, but underlying it's pretty much the same simple principles if you're going to the basics.
So if a machine can learn, that means a machine can also be intelligent? Martin?
I just wanted to add on Andrei's last point as well. So you know how people sometimes say that programmers are lazy? I think Bill Gates is brought as an example, like he was super lazy, so he tried to build computers to automate his job. So I'd say machine learning people are even lazier. They're too lazy to even program, so they try to teach the computer to program itself. So that's essentially what machine learning is trying to do. But yeah, as to your second question regarding intelligence, I would say yes. And any obviously we can get into the philosophical nuances of how we define intelligence, but for the practical purposes, any discussion that you have with the new GPT model should kind of confirm that.
Yeah. So, and then the next question would be for Andrei, and then I'm going to let Vlad ask his questions as well. Some of them. I have many questions. Just believe me, I have so many questions. My next question would be, so that means you're going to apply AI, but you're going to apply the version of AI called machine learning at Bolt. So what are the general lines where machine learning is used in practice at Bolt?
There are many areas where we found machine learning and even more generally data-driven approaches. So that might be as simple as uncovering some simple constants to add on top of some previously uncalibrated processes. That's not machine learning. That's just they're just like data-driven, building data-driven algorithms. But generally, we're finding plenty of use cases. We've seen generally that all classic processes built at Bolt have some parts that could benefit from data science. Some in a more critical way, some in a more optimization, nice to have way. But if I were to bring out the main categories, there would once be this sort of prediction forecasting problems, where, for example, you want to forecast ETAs, how long a travel is going to take, or some other forecasts, such as the forecasting of the food preparation time. You want to understand how long preparing your food is going to take for both UX and operational purposes. There are some other algorithms, some other class of problems where machine learning helps with optimizing our processes. For example, we're doing financial planning. We're forecasting how different markets would behave under different scenarios of investing money. Again, like a forecasting problem at the basis of it. But then we're looking into how to optimally allocate money in order to obtain the maximum revenue. So this is more in the area of business intelligence. I would say you're trying to understand based on data and forecast how to take optimal decisions. And of course, there are we have use cases regarding computer vision as well. We're doing we're processing the documents of our drivers, of our riders as well when needed, and we're extracting data to understand if it's the same person, for example, in the document as in a selfie they're taking. If we want to check that it's people who indeed have like a driving license, or who are indeed like people who've signed out to work with us. And of course, like natural language processing use cases, and that Martin can talk about more. We're trying to automate as much as possible of our customer support pipelines for a smooth experience, and we're seeing increasingly more natural language processing applications, especially like since the growth of large language models, but before that as well. So many use cases, really many use cases.
Yeah. Thank you. I guess Vlad is eager to ask his questions, at least one or two of them.
Yeah, sure. I have a few questions as well. I don't even know where to start. I obviously spend a lot of time in cars and in traffic, being in Germany, which is a really car-centric society, and everybody drives here, and generally long distances and so on. So everything that can make a trip shorter, or at least every time I can find out how long a trip is going to take before I get in the car, I'm totally in for it. So I just want to start maybe by going into a little bit more into how exactly this competition that you took part in, this algorithm that uses traffic cameras and intersections, how does it work exactly? So basically what you're trying to do is, by using let's say public data, because it should be public, right? I mean, it's traffic information from our cities, trying to estimate how long a trip is going to take, or when the car is going to get there, and so on. Can you please tell us a little bit more about how that works, how your algorithm works, or what is it supposed to do, and what is a gradient boosted tree? Because I've never heard of anything like that before.
So if you want to calculate the travel time between 2 points A and B, let's say even for Google Maps or Waze, when they do this, what you need for that is the underlying road network, or the graph of the city, where essentially all the intersections are nodes, and the road edges between the intersections, so we can call them streets, are the edges between the nodes. So this is basically like a mathematical structure. And if you want to calculate the full travel time between A and B, you need to perform a shortest path finding algorithm in that graph. So some examples of this is the famous Dijkstra algorithm. In practice, the routing engines of today use more advanced, more optimized methods. So in order to do that, you need to have like very accurate, basically first the shortest path algorithm finds the shortest route in that graph, and then to calculate the travel time, usually it sums up the edge weights. So in that kind of graph, the edge weight is actually usually the duration to traverse that edge. So if you sum them all together, you get the full time, let's say in seconds. And now in order to have an accurate time, you need to have accurate edge weight on all the road segments. So basically what that means is you need to be able, for every road in the city, and these roads can be very small, they can be like 10 meters, 50 meters, you need to be able to predict at any given time in the week what will be the time for a car to go through that road. So we built an algorithm that tries to predict that given some sparse data.
Okay. Yep. And how much, let's say, I read about this a little bit. So obviously not every city has all of the intersections. There aren't traffic counters in all of the intersections, right? So what do you do for the intersections where you cannot count the traffic? Do you estimate based on the other intersections where you can get the data, or how do you use, let's say, AI and machine learning for that purpose?
That's a good question, and this is indeed what we refer to as generalization. You're working under some missing data, and you're working to detect some patterns that you hope would generalize to previously unseen data, scenarios, in our case, intersections. How the setup of this competition looked like is that indeed we had some sparse data from traffic counters, which are devices working in the main intersections of a city. They're counting how many cars are passing nearby them. So that's not giving you any information about in which direction they're going or towards which road. They're just counting like how many cars passed through this intersection. And this was a source of data. It's open data shared by cities, some via API. And the other data that we had was some sparse measurements of traffic speeds at different streets, at different segments, at different times of the day. So the data that was made available for this competition also comprised this probe data, which was very sparse. It was tens, hundreds, thousands. I can't recall the number exactly, but I recall that it was like very, very low coverage of the street network. And we would get couple samples like in the city for different hours. We would know what's the speed that was recorded by a car at that point. So we would observe for given states of the city. We would observe that now we've got 10 cars passing around the traffic counter A, 20 cars around traffic counter B, 30 cars around traffic counter C. And then we've also observed some speeds, like on some street X, we saw a car traveling by 20 kilometers an hour. On some other street, we saw some car traveling by 50 kilometers an hour. But again, all of this is very sparse. And then this was all the data that we were learning from. That actually our algorithm was learning from. And then we had to build a method that, given only the counter state, so given only the observations of how many cars are at an intersection at the times of the day, would produce traffic estimates, so like travel time estimates for all street segments in the city. So the counter data was pretty much the same, both for the training time and this like evaluation time, because you've got the same counters fixed in the city. But what was the main difficulty, I'd say, is that during this training phase of the algorithm, you observed, like, for a certain hour you observed 3 street segments with their speeds, for another hour you observed other 5 streets, and then at test time, when our algorithm was evaluated on the competition server, you don't know which streets you're going to get to be evaluated. They might have like way better coverage, they might have like a proper big fleet, and in fact there was like a company providing them this data, some navigation company which had like plenty of data. they had like a lot of more data, and they were able to evaluate on way more streets than we've seen like a test time. So they would want to see how well such an approach generalizes. And this was the main interesting part of the competition.
Right. Thank you. That is interesting. Now I also have a more, let's say, tricky question. Not a trick question, but maybe a tricky one. In reality, as far as I know, I'm a really big fan of Google Maps. If I love anything in this world other than my wife and my mom, it's Google Maps, right? Because it spares me really a lot of time when I'm driving, especially here in Germany. A lot of accidents on the highways and so on. It redirects, it does all of that. And it basically does that using in-car data from other Google Maps users, and maybe not only. And yeah, okay. So what advantages would something like this have to just using in-car data? Does it have any advantages to use this sort of traffic camera data, adding it to all of the in-car data that you're already gathering? Does it bring anything new to the table, or was it just a theoretical exercise that doesn't really apply in reality, or is, let's say, it's no longer the case to use something like that?
So for this competition, we actually had access to both to some extent. So we had the counter data, but we also had the, let's call it, as you say, in-car data. It's just if you think about it practically, then of course Google Maps is a great product, especially if you can use it for free. But if you are a company, or you are a local city government, or someone else who for any given reason wants to develop a routing engine or a ETA prediction engine, then you will not have that real-time data, right? So I don't know if the Bucharest city government wants to do an ETA algorithm, then they won't have that. So the counter data is something that tends to be available. So this is public data. So this I think one of the stated goals of this competition was to provide like a very low barrier entry for anyone to do traffic prediction. But of course, in real life, putting these two data sources together will give you the best results. That's what we did here as well.
Okay, very good. So now I understand the reasoning behind it better, because in my opinion, what point does it bring to use traffic camera data when everybody has a phone and GPS, and you know every time at what speed the Google Maps or Waze user is traveling and in which direction, and basically you also know the destination. So more so than with the traffic cameras, right? You see a car in an intersection, you have no idea in which direction it's going. When you use Waze data, you know exactly where that car is heading, right? And in big picture, you also know the route it's going to take because you're telling it where to go, right? So that's why in my head, as a theoretical exercise, I understand it, but I wanted to know if that applies in practice as well, or if it really is useful. So I think I get it now. Yeah.
So usually in the traffic forecasting literature, it's still that the counter data is considered something like as a golden truth, because actually not in this competition, but usually the counter data can be directional. So it can count like both directions of cars going. And that like with counter data that it has counted all the cars in the intersection. But even someone like Google Maps, they maybe capture like 10% of the traffic in the city, not more. So they won't have the full picture.
Right. Okay. Well, no further questions at this point.
For now. But I do have questions, more questions to come. So the next one is for Andrei. So I've read loads of news in terms of how AI or machine learning was able to find new ways of resolving issues. So as far as I know, DeepMind from Google, they were able to identify proteins with an accuracy of 96%, for example. So, or NVIDIA recently said they are able to reduce the amount of time they spend on creating masks for GPUs, from 4 weeks to 1 day, something like this. And then there was another Google engineer. He tried to raise an AI algorithm in finding a new way to build a CPU. He spent 28 days, whereas the algorithm spent maybe 8 to 10 days. So I'm really interested to know, how is it possible that AI is able to resolve issues sooner than regular people? Because we're talking about really complex issues. Proteins are not easy to understand. CPUs, building those CPUs in all of these transistors and whatever, really not easy. And also what are a couple of surprising findings AI was able to bring out? Because I've been reading loads of news left and right. And then basically what I understood from there is the fact that sometimes AI is able to outline really interesting patterns, outline surprising ideas and things people weren't really thinking about. So yeah, my question is in two parts for Andrei. So yeah, how is it that AI is actually able to resolve some issues? And second one, what are the surprising findings you found in your own work?
That's a good one. I think the advantage of such methods inherits naturally the advantage of any computational machine. Like, of course, there's plenty of work that could be automated, that could be performed faster by machines, even without AI or ML. And we've already been running plenty of algorithms. We've seen, or we've not seen, but they were like behind many things that we're doing in our daily lives, in many decisions that are impacting us. Algorithms and generally like this computational approach and scaling up work that would otherwise be far less optimal done by humans. This is something that's already been happening for tens of years. So this is not something new. But indeed, this take on letting these algorithms become more creative, because so far it was mostly about telling what to solve and how to solve it. And rather just outsourcing the computation, or let's say these very, very algorithmical steps to the machine. Now you can rather pass a framework if you're able to pass it in the right way to these sort of learning algorithms. They might be able to discover how to solve them themselves. So this is the more let's say innovative part. And all the examples you brought up about the protein folding problem from DeepMind and the chipset optimization as well, the chip design optimization as well. These are like very, very surprising ones. And generally, it's mostly a matter of how you manage to convey the problem to such a learning algorithm. Because essentially, there are a couple of high-level approaches that have been working over and over again in generative context, generating, for example, as you've seen, like images as well or text. Optimization purposes, or like optimizing for a given cost function, you want to decrease it as much as possible by taking some actions. For example, in the reinforcement learning setup for self-driving cars, you might want to decide on which steps to take at each step of your driving journey based on observations you're doing. So based on proper framework that you're putting when running these learning algorithms, they're able to generate interesting stuff. And yeah, of course, I would say that generally all the interesting findings that I've seen hands-on in our work would rather be about this sort of better statistical understanding of data. So I can't say that I saw something really revolutionary in my day-to-day work where like AI really understood something that would otherwise be impossible for a human to grasp. It was rather this sort of usually the pattern is the following: we have some process that we want to build models for. For example, again, let's say like in the simplest form, let's say ETAs. You've got this pattern, this process. You want to forecast ETAs going from a point A to a point B. And then you're thinking like, what would be potentially impactful for this sort of prediction problem? And you're thinking, for example, that time of the day might be a good indicator of how long it's going to take, the estimated route length, the estimated count of intersections the car is going to pass through. So there's like this sort of, at least like in my day-to-day work, there was like this sort of human understanding of the problem. Then crafting the data set that an algorithm would learn from, and then when debugging, being able to go into what the algorithm has learned, because there are like some explainability tools as well, which allow you to understand at a high level how the method, how the learning has worked. You would see that some are more impactful than you believed in the final predictions, or some are less impactful. So while you might have your human biases of what would be very influential for certain predictions, than the way that the algorithm actually learns, and it performs well, like better than baselines or human predictors and so on. So like it's got a good reason to do so. You'd see that it has learned differently than you expected. And I think, for example, we even saw this in our traffic competition, because one of the features we were trying to put into our model was about the total traffic across the city, some averages of speeds, for example, or total sum of all counters in the city as a sort of indicator of how heavily circulated the city is at that point. And it pretty much didn't matter at all for our final predictions, which was surprising to us. We understood why, because we were already passing that through some other signals, so it was already information that it acquired. But for us, it was sort of surprising how like the overall city state doesn't impact firsthand the segment level traffic speeds, given the context of our problem.
Yeah, cool. So I want to ask Martin, in this case, let's continue with another question. My question is, how do you train such a machine learning? So Andrei explained a bit how you get to train such a machine learning, but do you need actually special programs? You need special computer? What's the special stuff you need to do in there? Because normally I'm doing in my programming work, I need to write algorithm, and I'm going to write them by hand because that's how life it is, until ChatGPT will take over my work. But we're getting ahead of ourselves. So what tools do you need to use, and how do you get to train? And what does it mean to train this machine learning? How do you call it machine learning algorithm, or do you call it machine learning program?
Model, usually machine learning model. So one of the nice things about our solution in this competition was that you can actually train our models on a MacBook laptop, essentially locally. There were 2 tracks in the competition. So for the smaller track, you can definitely train the end-to-end model locally. And for the larger track, you would need to make the data set somewhat smaller, so use some sort of sampling strategy. But otherwise, that was a nice aspect. And this is true for the gradient boosted the gradient boosted family of models that Vlad was asking about before. So essentially, it is a very efficient implementation of a decision tree ensembling algorithm. So you may have heard of decision trees in traditional computer programming, right? So what this algorithm does is it builds sequential decision trees, like a very large number. It can be thousands of decision trees, in a way that each sequential decision tree is trying to correct the errors of the previous ones before it. And each you can think of decision tree as a prediction algorithm, even an individual one, right? So you have branches in the decision tree, you have some terminal nodes, and now basically you give your input, what we call features, into the decision tree, and depending on which terminal node it ends up on, that will give you your prediction, right? So a very simple decision tree might have only 4 unique predictions, but if you build that very complex gradient boosted ensemble, then you might have millions of unique possible predictions, and then that starts to resemble more of a real model. And that's essentially the approach we used in this competition. Now, if we're talking about the AI world and like those massive AI models, then those are usually trained somewhat differently. So they're trained on a GPU, so a graphics card, or sometimes even a specialized hardware only meant for training AI models. And training them usually takes way more compute, takes a lot more time, to the degree that it can take weeks or months to train a model. In our case, the gradient boosted models we could train in a few hours, so that was quite convenient.
So the interesting bit with this is, so basically what does it happen? So you create a model, but you take real life data and you feed it to the model, and you don't explain to the model what it needs to find out. It's gonna somehow find out on its own.
So you would need to fit in both inputs and what is the expected output. So in our case, the expected output can be what was the actual travel time on a road segment, right? If you're building an AI model to classify cats and dogs, then the input will be the image, and the expected output will be whether it was actually a cat or dog. So by feeding examples on both sides, you're teaching the model to learn the function between, like that's all machine learning actually is. It's just a functional approximation from inputs to the target space.
Yeah, so basically, I've been hearing about Google search, like page rank and whatever they had. And as far as I understood way back when, they were basically using machine learning with loads of variables, like thousands or maybe millions of variables. What are those variables used? What do they do? What are they variables? If you were to recreate, let's say, Google search, what does it mean by having variables in there? I guess this is a question for Andrei now.
Yeah. I think I guess Google's first implementation of PageRank was mostly based on how different pages link to each other, what are the sort of relations between all the pages. And then they would be using, if I recall correctly, mostly linear algebra tricks in order to extract some structure from that and use that in their ranking algorithm, which I expect that in its initial forms, like it couldn't have been anything similar to the sort of rankers that we're having nowadays. Of course, I assume that the metrics they might be evaluating and the sort of high level objectives would be the same. But in the meanwhile, since the first versions of PageRank, which, if I recall correctly, made it to the linear algebra textbooks about how they were extracting those relations, what sort of metrics transformations they were applying. This got like eventually to be some sort of 101 introductory stuff about why linear algebra is important. In the meanwhile, there was a lot of more development in the learning to rank domain. And there's a big class of approaches of models about how to rank stuff as in a way as relevant as possible to a user. Given a query, for example, or given just the context of a particular user. For example, in certain setups, you might not even have a query, but you'd have, as you have like in our Bolt application, you'd be opening your app, and we might be suggesting you already 3 places where we think that you might want to go based on your historical travel patterns. So that's like query agnostic. We're ranking the most likely destinations, and then as you're typing like in a query, of course that would also be taken into account. But then there would also be this historical pattern input into the model, into a model that would decide how to rank these outputs.
And in terms of variables, is that correct? When I hear about training whatever AI and machine learning with, let's say, 1 billion variables, what are those variables? The 1 million variables, let's say you're training an AI model for image recognition. The variable is what? One piece of image, or what is that?
I think that in this context, there is the features that the model takes as an input in order to produce an output. And for example, let's speak like about the simpler case with ETAs. Those would be time of the day, for example, day of the week, start location, end location. These would all be input features to the algorithm. And then, having seen historical data, it would be able to produce, after learning, it would be able to produce some estimate. So those would be the training features, as we call them. And then the parameters that you have heard about, these billions, millions, and billions of parameters, this is usually going within the model. So certain models rely on plenty of parameters. For example, the model that Martin mentioned, the gradient boosted models, these are just like sequences of decision trees. Of course, you can represent the trees in various ways, but they don't have like these sort of numeric parameters per se. But the neural nets, which are the hot thing right now, especially like through the large language models, they do have many parameters. So it's pretty much a function that they have learned. You can think about it as any sort of classic mathematical formula that you've seen, meaning additions, exponentials, multiplications, and so on. And those formulas are parameterized by some numbers. And in the case of these large models, it can be millions, is already like small. It can be like billions of parameters. This is maybe what you've heard about. So this is going within the model.
But if you're talking about image models, then it's true, as you say, that if you have like, let's say 1,000 by 1,000 pixel image, each pixel is 3D RGB channels, right? So essentially, one image is 3 million numbers, and all of that goes as input to the model. So actually, images is something that only neural networks can handle. So I'm not aware of any other approaches being used for that.
Yeah, so in terms of neural networks, I guess the other question would be, of course, you have an image. As far as I understood, I was following a channel on YouTube called Computer File. I don't know if you know about it, which is a really nice channel. I've been following it for so many years, and they were explaining in general how AI is doing stuff. So they were saying AI basically goes row by row, and it's trying to understand what the full image, like 2D image, is in there. And basically, what they were also showing is the fact that you can trick the AI in thinking that instead of having a house in front of you, you have a cat or whatever, just by putting random dots in different places, random pixels. So how is it possible that AI is so smart and fast, but you can fool it with a couple of pixels?
Luckily, Andrei is doing a PhD on this exact topic, so maybe he can comment.
Yes. So these are pretty much the equivalent of what we humans see and deem as optical illusions. Same as we have optical illusions, you must all know, like those sort of classic illusions with circles and small arrows on top of them, and one might seem that is turning in some way and the other in some other way, while in reality, if you are not watching the arrows, they're actually still or turning in the same direction. So all of these sort of tricks that images, static or GIFs can play like to our brains, it's pretty much the same for the computers. Like what might seem to us as a very hard to comprehend illusion might be very easy for a computer to understand, to evaluate properly, and the other way around. Like what for us is like a very simple, very simply to say that this is like a cat, not a dog. It's just like this is just like a cat with 2 points on top of its nose or whatever. For a computer, it might be very hard, and this is an artifact of the fact that our brains essentially are not built the same as the neural networks. Of course, there is biological justification behind it, but they're learning some sort of functional approximations of these images. They're learning some ways to transpose those images into one of two classes. And the problem itself is like a very highly dimensional one. As Martin was saying, it can be like 1,000 by 1,000 images. It can have like 3 channels, RGB, and then you're already having like 3 million features as input, and you want to produce like only one of two outputs. Even visualizing it like in 3 dimensions can be difficult. Then imagine that it's actually like a 3 million dimensional space. You've got 2 areas, one being like the ones of cats, one being the ones of dogs. But then there are like so many edges and corners in that like million dimensional space you can't even imagine as a human. And always, no matter how cat an input might be, it would always, because of this high dimensionality, it would always be close to some corner, some edge with the dog class. And then it's only a matter of finding how to add certain pixels to move it to the other part of the edge.
Yeah, so basically we're landing in here. So basically a computer can be having an illusion. Now we're getting to the point where I've been hearing the last couple of weeks in terms of generative AI about AI hallucinations. What is that stuff?
Yeah, okay, I'll take that one. So it's actually a funny name because I'm not sure if hallucination is the best term to describe it. But the way to think about it is that and right now I'm talking about language models, right? So something like ChatGPT. If you ask it a factual question, then actually, even though in its almost limitless weights that Andrei mentioned, like it has been hypothesized that GPT-4 might have like a trillion weights, so like 1,000 billion weights. No one knows for sure, but it has a lot of weights. And there are some papers that show that some of these weights are actually holding factual information. So, for example, that Paris is the capital of France. There is some weight layer or vector inside the model that kind of retains this knowledge. But despite it being able to do that, it is still quite poor as a factual assistant. So it works very differently to how Google search works. So in Google search, you have like some set of documents that contains factual information, and then you do like whatever is the search algorithm, you do search against that set of documents, right? So in a language model, you're essentially just trying to generate the sentence where each word depends on the previous words, and then on the probability of this combination being likely in total. So what usually is meant by hallucination is that if you ask a somewhat factual question, then the model can provide an answer that looks very much like a correct one. But in reality, if you read into it, you realize it's total gibberish. And the easiest way to actually produce this that I have seen is ask the model to give you some scientific citations. And it gives like very nice looking ones. But if you then, you look up this journal and like, is there an actual paper on these pages? Just today, we had a case where we saw that there was no paper like that didn't exist, but it looked very convincing. So that's, I think, usually what they meant.
Yeah, that's really awesome, because we haven't yet gotten to the point where we have true AI and it's already hallucinating. So what's our future, Let me go to the other question before I'm going to let Vlad ask his next questions. So you were saying, so all of these models incorporate factual data. So that means all of these models, the better they need to be, the fatter they need to be, bigger in size, like actual size in bytes and whatever now. So is it correct when I think about my Pixel phone, which is using AI to improve my images, that means whenever Google wants to improve my Pixel phone AI for the images, then Google will need to load my phone with more data, bigger, more data. So is that correct? So because we drop in more and more factual data in those models, that means, one, how big those models could they get in our computers, for example? And two, is it possible to just get to a random bit of the data in there just by manipulating inputs?
Okay, I can take it. So that's a good question. That's an interesting take. What happens? Indeed, the more complex models you want, the more performant, the more well-performing models you want to have. Indeed, we're sort of at the stage where there's a couple of newly uncovered technologies, especially like when we're talking about NLP and computer vision. And we've indeed seen that making models larger means better performance in certain classification tasks or language generative tasks and so on. So indeed, it's right now, like we're at a point when the available technology wasn't fully exploited with the largest models. While if you are talking about some simpler approaches, you might see that at some point making the model larger, your approach larger, your billions of parameter more, you'd run into some plateauing effect, and you'd say that, okay, like it doesn't make sense to increase it further because it's just like extra training cost. It's taking larger storage, for example, as you were saying, like for deploying on your phone. It doesn't make sense. Right now, we're not at that point. There are of course, like in between, like this GPT-3, 3.5, 4. There's of course like some changes in the methodology, but pretty much as far as we know and suspect, because we don't know like what GPT-4 exactly is going to do, but as far as we know and expect, it's pretty much the same basic underlying principles, but just putting more computational power, more numbers into it, more parameters into it. Now about this one-to-one correspondence with factual things and with factual data and the actual parameters of the model. Them learning this sort of like learning implicitly this factual information in some archived way, because that's essentially like we're talking about archives. Learning that factual data within those parameters somehow is rather an artifact of the training process. So those were trained in some way that meant that they have to remember that in order to be able to answer to further questions. But it's no guarantee on the fact that they've learned those facts properly, or that they would be able to. They would be able to. Of course, they would never be able to understand when they're not knowing things usually. So there is indeed some relation from this point of view. Of course, like the larger model, the more facts you can store in it. But then it's mostly it's also like a matter of how good your model is, and these models seem like very, very capable. because essentially you can think that if you have like 100 bits, you can already store like 2 to the 100 different binary strings in those like 100 slots, which is already huge. You can think like about 1,000 or 10,000, and then it's just like an exponential, like to the power of that. So it's not as much, let's say, a matter of the larger models. It means we store the more factual data. It's just the larger models, the more complex things they can learn become, and apparently with these like GPT models, the more accurate they become, which is not necessarily like the general truth.
Yeah, I'm thinking about, let's say, Google Pixel, and then also the drivers, the NVIDIA drivers in my video card, for example, because they tout the AI in DLSS, how they can improve or even invent new frames. DLSS 3 is practically inventing new frames in between frames. So that means they also need to hold their own data, historical data and facts. So how big would those models be? Like 100 megs, 1 gig, 5 gigs, something like this? How big could such models be?
I actually know a person who works at Microsoft Teams doing audio, basically echo, cancellation, noise suppression, and their ML stack, AI stack, works on the edge. So it works on individual devices, so phones and computers. So that model is actually relatively small. I think it's less than 1 million parameters, last I heard, which in deep learning neural network world is really tiny model. So it's working in real time, and it's I think it's doing it can do like 100 frames per second in inference or something like that. So it's very, very fast.
So, but we don't really know the size. Let's say, for example, I'm taking many pictures, which I normally don't do, but I know people who take so many pictures, they barely have some space. So if Google, for example, wants to do an upgrade to their own AI in their Pixel phones, they will occupy much more space. Do we know, like, how much actual space would such a model occupy? Like 100 megs, 200 megs, stuff like this?
It depends a lot on the model and the task, but I can bring a concrete example. In our rentals team, we're also building this scooter classification model. At the end of the ride, we ask our users to take a picture of the scooter if they want to park, if they want to end the ride. And according to different markets, there are different rules that we have to follow, such as the scooter has to be within some bike parking zone, for example, or it has to not block sideways entrances. It must not block streets like cars. So we mandatorily ask users in some markets to take pictures of the scooters, and then we want to classify whether it's a good parking or not, considering historical labeled data that we have. And I guess those models which perform very well and which have helped us decrease bad parking rates in some Nordic cities by more than half, those I think are models in the ballpark of like 50, 100 megabytes. And we're still running them. We're running them on our side in order to keep the application as light as possible. Indeed, as like a very good consideration. But we're always looking into making them smaller, but not too big of a trade-off in terms of accuracy, and putting these sort of models on the edge just to allow for faster processing, smoother UX, allowing our clients to end their rides faster and so on. But if we were to do that, which is something we might consider, we know that these models start from, like, in this scooter parking classification case of pictures, start from a ballpark of like 50, 100, perhaps slightly above that, but not huge sizes. And we also know that they can be optimized. So far, we didn't care so much about optimizing them, running them on our end. But if it were the case, it would certainly be like a very, very important thing to be able to not put too big of a load on the client side from a storage point of view.
Yeah, that's an important stuff. Although in the future we're gonna go and have much more space, simpler, like cheaper space in our phones. That's why maybe in the future we're gonna have phones with 10 terabytes of data, and out of which maybe 5 terabytes will be different models, visual models, language models, whatever. And you're gonna have like a super duper AI assistant with you. So I'm gonna let Vlad also ask his questions, because someone needs to stop me.
Yeah, very heated discussion. I knew this was going to happen, but it's good. It's nice to have such high level discussions with the people that are talking about, and not just opinions like we usually do. But I do like having opinions, and one of my opinions is that ride sharing is a very beneficial thing. I mean, I don't know if Bolt is ride sharing, but this sort of alternative to taxi is something that I like to use, and I am a Bolt user as anytime that I get the chance, especially when I'm back home in Brașov in Romania. And basically, I have a few questions related to specifically to Bolt or to this sort of application of AI and machine learning. And I'm curious. I've been in a lot of countries around Europe, and each country has its own specifics when it comes to driving in particular, right? And to traffic and something like that. And traffic is bad everywhere. Traffic is bad in France, and it's bad in Germany, it's bad in Italy, it's especially bad in Romania. But each country has its own specifics when it comes to driving and to the way people behave in traffic and how fast they drive, how slow, how much attention they pay, and so on. What I'm trying to get at is when you train an AI or when you use machine learning, can you do one algorithm for all over the place? Or do you have to do one algorithm for Bucharest, for example, and you have to train on a different data set for Tallinn or for, I don't know, Paris, right? Or does it work? Are we so predictable that you can just take a mixture of data and then you come up with something good that works for the whole of Europe, let's say, or for the entire world?
So we have a lot of models, as Andrei mentioned before. For something like traffic forecasting, ETA prediction, we definitely do separate models per city, because a city tends to be like a self-contained unit of complexity, essentially. So like you can imagine that what our models do there is kind of really learning the driving behavior on one specific intersection, and this is like super city specific. But then we have some other models, for example, like let's say fraud, trying to predict fraud, credit card fraud transaction rate. So there we can already see very common patterns of fraudsters, maybe even across cities and across countries. So there we actually have a common model, I think, last time I checked.
Interesting. Okay. I was curious about that because, I mean, particularly, every driver, it has to adapt, or he or she has to adapt to the city they're driving in. And I was curious if there is a way that you can predict every sort of driving in every city in one single algorithm, or if it's more complex than that, right? But I guess that answers my question. Another sort of dumb question that I have, I'm not an expert in the field, but how do you know when your AI is properly trained? Or is there such a thing as overtraining an AI, right? So we're talking about diminishing returns. At which point do you know you've trained an AI enough and there's no point in going any further? Or when are you sure you have done everything and you're not missing something out?
That's a very good question. So indeed, because of this iterative process of learning, you cannot point to learn too much. In the worst case, your algorithm can become like a lookup table. It would overfit, and it would say, for example, that for any input it gets, if it's exactly some input that it has seen, then it would output whatever it has in a training time. For everything else, it would output some random value. And from some point of view, like that would be learning exactly by heart the training data it has seen. So that's a risk. This is what we call overfitting when training these algorithms, and when not generalizing. So this is why there are certain techniques to make sure that you're not doing this. So usually you're splitting your data in certain chunks. Most often, and the simplest way could be splitting it in a train and the validation set, and a test for further testing after the training process was done. How you're working with these like main two bits with the training part, which can be 70%, 80% of your whole data, is that you are training your model iteratively on it and only on top of it, but at each stage or at a couple of stages of training it, you're keeping an eye on how it is performing on this validation set that was left out from the training algorithm itself. And then you're seeing that your algorithm would generally monotonically be decreasing in terms of error on this training data set. But at some point you'd see, of course, like it might start plateauing on this data set, but what you would see on the validation data set is that at some point it would plateau or even start growing. And that's like a sign that, okay, your algorithm is learning some patterns in the training data set that don't exist in the validation one. It's actually hurting the performance on that not trained on data set. So it means that you're overfitting right now. You should stop. And then you're stopping. It means that your algorithm has learned the much that it could from this data and from your model. And that's when you halt this iterative process. Now, in terms of not being able to do better, this is there would always be some error, some noise that you can't reduce. There is some non-deterministic component that you would not ever be able to model. And you might be reducing error further. Even in this case, if you add more features, you come up with a stronger model than the one you were already training. But this is more up to the human expertise to understand if there's like indeed a good use case in improving the model further, in bringing in more data, and or whether you're already like in that part where you can't reduce any more the error because it's just like unpredictable noise. Of course, you can understand when to stop early. If you're, for example, if you've built some algorithm, it reached some error level, and then you've only got like 3 potential ideas ahead. You're trying all of them. They're intensive, and you're seeing that the error only decreases by further 0.1%, 0.01%. If those are like your best guesses, it's usually a good sign that you have to stop. But you always have to take into account what's the business impact of the additional gain you would get. Because maybe there can be cases when even like that 0.01% is worth it, and then you spend like proper long research effort on finding something better.
Okay, cool. Maybe one more question related to the subject or related to Bolt in particular. This might sound like a dumb question, but I am curious because I'm not always, I'm not in the field of AI, so I sometimes wonder how much good does it really do in a company? So the question would be, how much does it change a business like Bolt? How much use is AI in comparison to old-fashioned IT methods, right? So let's say computers have gotten stronger and stronger and more powerful, but would it be the same if you would use, I don't know, regular computational models instead of all of this AI stuff? Because AI has become sort of overused, in my opinion, right? So some people call AI stuff that isn't really all that intelligent because it sounds cool, right? So obviously you're not doing that. It's a really high level of science here. But how much does it change a business like Bolt? How much does it help it comparing to how they used to evolve before AI was such a thing?
Yeah, so actually we do use the classical algorithms as well. And that's why before I mentioned the distinction with machine learning and AI. So in practice, we never call anything AI in our work. We usually use that term in other content. But I think the comparison with like more traditional engineering approaches, you can think of it in a way that if you can solve something with if-else, like a simple logical clause, then that's fine. And you shouldn't use machine learning everywhere. Actually, there's a famous, I think now from multiple years back, there's a very famous Google guide on how to do machine learning. And one of the first rules there was that, if you can avoid machine learning, then at all means, please avoid it. So I agree with you. It's just that if the company becomes more mature, then what machine learning provides is, an optimization opportunity here and there. And it might be a relatively small opportunity. It might be like, let's say 5% here, 3% there. But if it's 5% of your revenue and you're like a multi-hundred millions revenue company, then that is already very, very interesting to the company. So I would say that's the stage where you want to start scaling your machine learning team. And that's kind of the stage where Bolt is now. We're actually seeing the machine learning team growing faster than the software engineering team now. Because all the basic functionality is built, but now it's a question of how to optimize that functionality more and more.
Right, that makes sense. Thank you. Well, maybe I have another couple of questions, but they're really general questions, nothing related to Bolt or to your activity in the company. Up on this point, obviously, I would really like to touch a little bit on ChatGPT. I don't want to go into specifics, but I do want to know is your opinion on what's happening in the last few days, meaning you probably heard of the ban in Italy and the fact that a lot of, let's say, very, very highly regarded people are writing open letters and trying to get it so that this sort of
that's
AI,
funny. Yeah, that's really good. Yeah.
Yeah, so that this sort of AI, that what the ChatGPT is better regulated and it doesn't get the chance, let's say, to do whatever it wants, right? So what's your opinion on that sort of thing?
I might be mistaken, but I think the Italy ban might have been because of data privacy reasons. I'm not like fully
Correct.
It might be like a partial measure until they're making sure that it's fine from a data privacy point of view. And from this sort of catastrophic looking at it, that it might hurt the society. It might become this dystopic Terminator that would eventually kill all of. I mean, of course, there's like concern about this in society as well. But generally, I've seen an interesting take from Jan LeCun, which is like one of the best, if not like the father of modern machine learning researchers. So he was saying that this is quite comparable to what was happening during the Dark Age when science was being punished and pushed away because it was scary.
And if you were smart, you were a witch.
He's like pretty much being afraid of new technology, being afraid of what you can control, and of course, like at a human and government level, but then also like at a company level, because perhaps companies have signed that open letter as well because they're left behind, and it's sort of like okay, everybody stop until I can understand it as well, until I can have a competitive edge as well, and then okay, now we're fine, you've waited for me, we can resume. Of course, there might be bad implications of it, and it's pretty much the same with any technology. Like when you're inventing a hammer, you can beat nails or you can go after people, hitting them with the hammer. So it depends like a lot on how you use, because of course, like it opens up room for easier fraud because you can automate. And we've seen it like with generative AI for creating fake profile pictures. You can generate plenty of content. You can automate it. You can make it seem like you don't need like anymore the troll factories where somebody would actually be staying and creating plenty of content just to look legit, which was low quality content, by the way. So like the content that could automatically be produced would be like way more legit from many points of view. You could have plenty of albums of certain persons generated with generative imagery. You could have plenty of content along some tracks of thoughts. So it could be somebody who's consistent in their thoughts just by automating these generative processes. And then you could use those to get into certain Facebook social circles, for example, be able to influence messy selections and so on. So there's clearly a risk with it. There's also like a risk of data privacy because people are assuming that it's like their smart private friendly sort of like open models that are available online via an API. And they might be pasting their like confidential stuff from work, secret personal stuff from their lives. They might be using it as this sort of like, again, like friend who is very good at keeping secrets and very smart and helps them. But in reality, the data gets processed somewhere. So it's out there in the wild. You don't know what would happen with it if it's not, let's say, properly monitored and enforced. So my high level take on it would be that it's technology. It's just a very important advancement in technology. We have to take it as it is. We have to understand where it might hurt us and maybe regulate it better. But it's by no means something apocalyptic.
Yeah, Bill Gates has written some stuff recently, and he was comparing AI revolution we're having around this time with internet revolution, and he might be just right. Not because he's Bill Gates, but we can see that this technology is able to improve. And basically, number one driver of this technology is productivity. That's why you do it. Not because it's fun. It's fun as well. But companies invest money in stuff because it's driving the revenue up for them. So that's a good enough reason to see. And we spoke in this podcast over and over again, like with any innovation, normally people overestimate the impact on the short term, but underestimate the impact on the longer term. And that's kind of hard to grasp, because initially you feel like AI is hitting you in the face, but then once AI becomes like part of the technological furniture, everyone forgets about it. Oh yeah, we have AI. Okay, this model, it's like 1 million times stronger than what we had 10 years ago. Who cares? We're going to continue our life. So it's just life. So let me continue with my questions, because I have a couple of other questions. So you were speaking in here about neural links. So let me understand. Isn't maybe it's better to say machine learning instead of AI? Should we change our vocabulary in this podcast? Because from what I understand from you guys, it's no better to say machine learning than AI. So I guess that's my first question, and then I'm going to continue with the next one.
I think if we're talking about something like ChatGPT, it's fine to call it AI. If we're talking about our small traffic model, then maybe that's more machine learning.
Okay, good to know. We're gonna choose when to speak about it. So let's say, in general, AI, isn't it able to run on regular CPUs? Because you said the neural net and whatever. Isn't, let's say, one CPU and then you link it with many other CPUs? Aren't those able to run AI just fine? Why would I need a different architecture in terms of computers and whatever?
You don't. So there's a difference between training the model, which is usually much more compute intensive. And this is what you do on GPUs, the graphics cards. And then there's just what we call inference. So that's using the model. So if you're talking to ChatGPT online, there's no training involved. That's purely inference. And recently people have shown that you can take I think this is Meta's large language model called Llama. You may have heard. So that's a 65 billion parameter model, which is roughly, I think it's like 3 times smaller than GPT-3, so the previous version of GPT. But it's still a very massive model. And people are now managing to run this on a Raspberry Pi. So I think it's very safe to assume that in the future, language models will be everywhere on all kinds of devices, small and big.
Yeah, because somehow initially I thought, okay, if you want to have AI on your computer, you need to have the latest neural link stuff. There are different CPU architectures running right now. They do silicon photonics. There is the classical CPU stuff, and then they want to build something like neural link, something like, not neural link. It's the Musk stuff, not the wrong stuff. They want to mimic somehow the neurons, but in the actual CPU. So I simply forgot the actual name of that CPU style. And you have all of these other bits. So if you're telling me, okay, training takes more time, but actually using the model is as simple as slapping it on a machine with a regular CPU, then yeah, the future is it's here even before us actually noticing it. Yeah.
One of the most exciting things I've recently seen is that there were some researchers from the US, so from schools like Stanford, Berkeley. They took this Llama model, which is the Meta model. But the problem with that model is that it's like GPT-3, so it's not a chat model. It's a model that purely predicts the next word, which means you cannot give it tasks. So you cannot say that, write me a Python program. You can only say that, like, this sentence starts like this, and it will try to complete it, which is not so useful. So what they did is there's this website called Share GPT, where people post their conversations with ChatGPT. So usually they share it if it's like it has done something impressive. And they just took I think it was like 70,000 conversations from that page, and they took this open source Facebook model, Meta model, and they trained it for 1 day for a total compute cost of $300. So that's $300. And they managed to show that it's on par now in terms of chat capability with Google's Bard chatbot, which Google, like a multinational corporation. So that was super impressive.
Yeah, so basically we find out that AI models can be loaded on client machines small ones, and then they can be easily run, and they can also be cheap. All of these are properties of stuff which can be easily integrated in the future technology and current and future technologies. That's why I want to get back to Tesla, for example. So what they want to do, they are trying to create a visual learning model, something like this, and then they will upload this via Wi-Fi. Basically, they're updating it via Wi-Fi. So it's really interesting the way they use also regular users to train the actual model in their life. So then that means we're really close to actual future, because all of these properties, like being small in size, cheap to use, and cheap to actually train, then we're closer to the future than I actually thought before we started the discussion in this episode. So my next question is, before I let Vlad ask his one or the other questions, my next question would be, I've been hearing about different research studies about the fact that you can poison an AI model and then force it to spit back data which has been used to train it. So how is it possible? So we're learning new stuff. Like it can, AI can have hallucinations, can see illusions, and now we hear that AI can also be poisoned. So what does it actually mean?
That's a really good one. And there's actually a field about this, which generally talks about how to hide training data or personal data if it was trained on personal data, while still building some interface, some algorithms that can satisfy useful queries. And there's like an example of, let's say that you've got some database with the weights of different individuals, height, any other medical data, but let's say only weight for now. You have like this database, and you would have it in some secured place, and then anyone interacting with it would only be doing it via API. Let's say they would have this way of querying it. Let's just say like get weight of some user ID. That is already like access to private, to personal data. You don't want to do that, but still, let's say that you'd want to allow people to access somehow your data, at least statistics of it. And then what you might do in order to make something useful of it, or providing some sort of useful access, would be, okay, let's only expose an API which would be giving you the weights, the average weight of any group of, let's say, more than 20 people, such that you can't tell about any individual of them, any individual one, how much they contributed. And then, of course, the simplest thing that you can do next is just like ask about the average mass of a random data set of 20 people, and then ask about the average mass of that same data set, but union with somebody you want to find something about. So you want to find their mass. And then you just got like the average of some data set, then the average of the data set union some particular individual, and then you can write the maps out and find the weight of that particular person. And it's like the most basic example of how only by allowing some aggregate access to some data structures, to some databases, you can find stuff about individuals. And these being the simplest ones, there will have been like when exposing such, let's say, statistics APIs, people are thinking a lot about what personal data might be leaking in this way. Is there like some risk about it? They're proofing their solutions for them. But in the end, it's like a cycle of attackers becoming smarter than people who are defending them, and the other way around. And then this naturally transferred into machine learning. And there was research about how you can make the model spit out the training data, and eventually you can write it as some mathematical. You can write in some mathematical formulation that would help you recover some of the training inputs. It's pretty much the same privacy considerations and same sort of privacy research field behind, but of course it's subject to way more mathematical take about how you can recover the training data than the simple example I gave you for a deterministic algorithm.
Yeah, that's really interesting, because from this point on, in terms of poisoning the AI model, you get to the point where you can actually hack the AI. Basically, we had an episode about that, like hacking the AI, and I guess these two are pretty much related in terms of wanting to do, or maybe not so much, because when you hack the AI, you want the AI to do stuff it wouldn't normally do. For ChatGPT, for example, there was the example with Dan, D-A-N, like present the alternative where ChatGPT would be able to do stuff it would normally not be able to do. So I guess, is it connected with the poisoning stuff in terms of being able to hack the AI?
I think you're talking about the jailbreaking mode, right? Or
exactly, jailbreaking. Yeah, I called it hacking, but I guess it's more correctly to
it's pretty much finding ways to take it a lot of patterns it has seen, take it like to some state that it has never seen before, and then working in this like very out of distribution state. It has not seen like anything like that before. Then you can take it like along some interesting new paths to have fun with. This is why generally you want to be able to guard as much as possible, to have some safeguards, some safety nets to your models as much as possible. And this might help, even like going a step back, this might even help with guarding better against these poisoning attacks for recovering training data sets, for example. If you, for example, only expose, let's say that you have like some picture classifier, let's say some computer vision model that, given a selfie of yours, it would give or not give you like access to some database. So it has embedded in it some faces. It has to memorize them somehow, but you're only taking a picture of yourself and seeing the output. If you had access to like the whole model, there might be like easier ways to get to understand somehow what data it's been trained on. This is what's called white box access to the model. You're getting access to its internals, to how it works. You're seeing the numbers. You can't easily make sense of them still because it's like a bunch of numbers, but it makes your life much easier in any mathematical formulation that would help you recover the training data. And then there's like the black box model, which is usually the case in real life, where you're only accessing via some API. You only got access to like the final outputs. And then it makes the attacker's life way harder, but it's still feasible. Adversarial attacks that we're talking about, like confusing cats and dogs, for example, work very well in this scenario. I'm pretty sure that there's like literature about how to recover training data as well for black box models. I'm not like into this field. I'm more like into the one of adversarial attacks, but I'm pretty sure there must be something about it as well. And then you're thinking how to convey the minimal information that would still be functionally okay for the end user, but let's say guard as much as you can your model outputs. You can do, for example, you might just answer to somebody querying this computer vision model. You might just say yes, like access granted, or no, access denied. You won't be giving like any probabilities or anything. This is some initial way. It can also be fought against. So there might be like smart things to do in terms of the input you're giving in order to essentially recover something useful about the training data. But yeah, again, this ends up in like a cycle between attackers and defenders trying to make their attacks better or defend their models better.
Like cybersecurity, same stuff,
Exactly. It's almost one-to-one with cybersecurity from this point of view.
Cool. Thank you. Vlad, do you have other questions? I'm going to have only 2 final questions after Vlad.
I don't even know how to follow that. The discussion is way over my pay grade at this moment. But that's good. I like it like that. But like you said, we're getting close to finishing here, and maybe first of all, thank you for a lot of the information that you gave us in this podcast. It was really interesting, and we never had the chance before to talk about AI and machine learning at this level until today. Maybe from my side, a couple of more general questions regarding the field of machine learning and AI in general. I'm always interested in how people can get into this field, right? Let's say I'm a young kid, I just finished school or high school, and I hear about machine learning and AI on TV all the time, and I'm interested in the domain and I want to have a career in it. How should I start that? Where should I go?
Yeah, so I actually know a few very well-established ML engineers here in Estonia who even haven't gone to university, but I have to say this is the exception case. So generally, people in our team tend to have a master's degree. Some have a PhD, or as Andrei, a PhD in progress. And usually it's in a quantitative field such as computer science, statistics. My own background is in economics, still somewhat quantitative. There really isn't. Okay, these days there are even specialized ML programs in universities. So obviously studying that might be a good entry point. But usually just computer science, which is also like the entry point for many software engineers. That's good as well. At least in Estonia, many computer science programs these days, they offer specializations in machine learning modules. So you can take some courses in that. What definitely helps, and I would recommend for juniors as well, is having a portfolio with like a few projects to show that, I built this, I built that. I tinkered a bit with machine learning models. That's a good signal that, first of all, you're interested enough and you actually have built some hands-on stuff.
What about in Romania in particular, Andrei? Are there any good programs at this moment in this direction? Or do you think, really honest, do you think there's any good programs at any university that you know of, or rather not?
There are increasingly more opportunities to learn about AI or machine learning, like formally in the academic institutions in Romania. There is dedicated masters. I know at the University of Bucharest, at the Polytechnic Institute, there is dedicated programs with good professors. There are strong researchers. There are research teams that are working increasingly more on these fields, and they're getting published at international well-known conferences. They're getting citations. They're getting impactful work. What I've seen recently is that it's usually professors who have some experience abroad, be it working, learning, doing their PhDs, masters, doing some research programs outside, and then coming back, getting involved in sometimes in both academia and in the industry, starting their own startups along these some AI technology, or just getting involved as a consultant in some other startups or larger companies. So I can see that the trend is like definitely good towards the best. And I know that, and this is a good thing. Don't take it for wrong, but I know that some professors are even starting these new courses, but by taking literally the same slides and courses from open MIT lectures or open Harvard lectures, Stanford ones. And this is not a bad thing. Like when you want to start something new, if you're like a very good researcher, you're understanding it well, let's go through this content because this is like top class. Then we can calibrate it as we progress according to the background of the students, according to how complex it might be. But I think it's like a really good starting point, and I'm seeing it way more often.
Well, that's good. I mean, work smarter, not harder, right? If MIT and Harvard are already doing a good job, why start over? As long as you're using those sources and not, who knows what obscure papers or something like that to teach, I'm fine with that. And of course, I mean, I'm expecting Romania to have a good program in this direction, given the high number of IT experts in the country, particularly in Bucharest at this point, and not only, basically all of the other major cities as well. Good. Well, I'm glad to hear that. And what can I say? I think I just want to thank you all for taking part in our conversation. And I hope we can keep in touch. I'm really interested in the subject myself.
Cool. I guess I can continue with one or two final questions for this episode. We're already 1 hour 30 minutes in, so thank you for your time. One of the questions is, how much do you think jobs in general will be affected in the near future meaning 1 to 3 years, by ML and AI? Because you see loads of articles all over the place. Everyone will lose their jobs in shirts, and everyone will stay somewhere at the corners of the streets begging for food. So what's your take on this, Martin?
I'm very happy you finally asked this question. I wanted to throw this provocative thought out earlier. My current thinking is that I think, let's say by 2040, programming as we know of it today won't exist anymore. And that doesn't mean that, current programmers will be begging for food. I actually am pretty optimistic about society's ability to adapt to the changing job market and all that. But what I think it will mean is that the interface that we communicate with a computer, it will be much closer to natural language. So there will still be a programmer of sorts, but it won't be that, they're writing everything from scratch. I guess that most of the code that's being generated comes from some sort of model, and then the programmer is there to kind of adapt it to the specific use case, maybe show some more examples, like how should the model solve this problem and so on. So definitely I see a very large change in that direction. And to exemplify that, at least in my job already, I'm using Microsoft Copilot every day. I'm using ChatGPT every day.
I want to use Microsoft Copilot as well, but they didn't implement it in at my workplace yet. I'm curious about it. We spoke about it a week or two ago, I think. Yeah,
it's really, really good. So I recommend trying it out. ChatGPT is something that you need to give it a task. You need to say that write this function. But Copilot manages to kind of scan your whole code base and suggest autocomplete prompts for you. So that's super useful. So definitely already seeing very large productivity gains, maybe to the extent of like 30 to 50% of my own work. So very optimistic about how this is going to change programming productivity.
Yeah, I guess I spoke about this sequence. There was a sequence in a Marvel movie with Iron Man where the main character was speaking with Jarvis, and he was telling to Jarvis, hey, please create me a tube. Okay, move this tube in the other, and then create some whatever link. Okay, now add me 2 programs and to whatever other stuff. So possibly that's what the feature is in terms of programming. That means you still have to understand the program and be able to debug it if something is it's not working correctly. But you will still simply be able to ask the AI, okay, build this, and then I'm going to review it, and then we can continue. In my view, it is pretty much like moving from from assembly language, where you write all of those instructions one by one and memory pointers and whatever, to writing something like JavaScript, which is quite high level, So from JavaScript, then you move to some other stuff like simply speaking with the computer. So it seems like a natural progression for me.
Yes, I agree. That's a very good comparison. I'd also consider it just a new abstraction layer that is meant to make life more convenient.
Yeah, that's good. So my last question would be, so one of the things, what, let's say, books can someone read to learn a bit more about AI? Let's say they don't want to go in to do computer science. They don't want to really go in the weeds of computers and, let's say, data science and whatever. What books or podcasts or movies would you recommend people to follow so that they get a better understanding? Because our number one rule in this podcast is to explain technology and make sure that people are not afraid of technology, but they kind of learn to appreciate it and use it. So what kind of sources, so for you, Andrei and Martin, what kind of sources should people read and follow to get more accustomed with AI?
I think first it's most important to get a grasp of what the field means nowadays, where it's applied. And by nowadays, I mean like over the past 10, 15 years. And I think that's easiest to acquire by reading blog posts, by looking up on, for example, there's this well-known competition platform called Kaggle, where different people or institutions are holding prediction competitions where you're getting, again, like some sort of data sets as the ones we're talking about, and then you have to produce some models to forecast on some previously unseen data. And there are some very well-known competitions, such as the Titanic data set, where given the characteristics of people on Titanic, you have to predict whether they survived or not the Titanic incident, and stuff as random as this. And then there's plenty of work that's openly available of other people of how they approach this problem, how they loaded the data, how they explored the data, what were the sort of things they were looking at. Are there outliers? I mean, are there people of over 100 years? Are there people below 0 years? Just to understand how clean the data set is, how good it is. And then starting to find manually some patterns, or using some classic algorithms to find these patterns automatically. So I think that's quite hands-on and easy way to get started.
Me, myself, I'm more of a theory-driven guy. I wouldn't recommend starting it like this, but I've got like my own, let's say, my own starting point into this journey was mathematics, and I'm more theoretical at heart. And then I found it a bit more natural because of my background to first go through some proper lectures at university, which are more theoretical, read some more theoretical books. There are like some classic examples like statistical introduction to machine learning or machine learning probabilistic approach from Kevin Murphy, if somebody wants to look it up. These are like very good starting books, I would say, and they walk you through the fundamentals, through proofs. They give you like a good mathematical understanding. And for me, like, I think like first I was doing like a lot of machine learning on paper, like proving stuff and so on. And for me, that worked out well, but only because of my background. And maybe I would recommend like people coming from Fs to do the same thing. But usually I would recommend starting like in a way more hands-on approach, going through these standard tasks, understanding what they require, seeing what models others used, then Googling them. There's like plenty of high quality content on blogs of professionals that explain why certain models work in certain circumstances, how they work. If the mathematics gets too heavy, I'm pretty sure they're still explaining what's the understanding behind them. Same as Martin was explaining how gradient boosted model trees work. They're building these decision trees iteratively, trying to correct on the errors of the previous trees. There would be explanations like this about pretty much all models you'd find this way by looking at open work done by others on some competitions, for example.
I would add to the practical approach, like definitely agree that I think most people learn better from practice, and especially with these AI things. I mean, these are very cool applications, right? So it's easy to get people excited. I would recommend to check out the repository on GitHub called Hugging Face Transformers, which has 90,000 stars, I think, and the accompanying website as well. Basically, you can get started with an AI model in an afternoon from that website, and then afterwards you can read up on how it works and all that. But just to get excited about like what you can do with these new and novel applications, Hugging Face is really cool.
Would you need any sort of programming language knowledge in order to start with this? And if yes, what languages are better suited for machine learning?
Machine learning is almost exclusively done only in Python. So just that's something to keep in mind, yes.
Good. Yeah, that's what I wanted to know. Cool. Thanks.
And in terms of resources, there's like this open thing from Google called Colab, where you can spin up a notebook. You have some cute, really decent resources to try out your models, to load data, try training something, even have some access to some simple GPUs. So the barrier of entry is quite low. You might even get started without any local setup if you're not like too much into setting up your local environment before trying something out. You can spin up a Google Colab notebook, get some solution from online of people classifying images of cats and dogs or solving the Titanic task. You can pretty much copy paste it, understand it line by line, get it running. You'll see that you've built like an AI solution. You'll be excited about it, and it will most likely get, if it's the thing for you, it will most likely get you to start learning more.
Cool. Yeah, that's the future, honestly. And I would say, and we're gonna finish here, I would say we will hear much more about AI as soon as possible, maybe in the next couple of years. And the last point, the last maybe question for both of you was, okay, how did AI help Bolt in general, the company you're working at? Martin.
That's a good question. Well, I think we have almost precisely about, let's say, 55 machine learning models in production today. So that means 55 separately validated projects where we have verified that there is some measurable improvement in some metric that is relevant and important for our business. So in order to fully answer that question, we would need to sum up like what's the total value in all of that. I'm fairly confident that it's quite a large value already. So there are different levels of AI maturity in companies. And actually, many companies are in the stage where, people are not sure like how much value is machine learning now providing. So they're always in this kind of an environment that's uncertain, like, and you need to convince people, and you need to always be showing them that, this can be valuable, this is promising. We at Bolt, we're rather at the stage where we have already measured and shown the value, and now it's the stakeholders, maybe product managers, who come to us like, what else can we do? Please show us. So
it is indeed a very, very well established domain already at Bolt, data science as a whole. And indeed, if you were to start quantifying all the measurable impact that we had, you'd get some, undisclosable, but like huge amounts, huge percentages of impact in terms of our business KPIs. And of course, they're like individual models, which help with this directly by helping with getting a better conversion, getting larger, for example, in the case of Bolt Food, getting higher total average cost of the things that clients are ordering. But then there's like also like quite a lot of impact through savings. For example, we'd have to call Google for their ETAs, for example, or any other third-party provider. Otherwise, if we didn't have our in-house traffic forecasting machine learning models to help us with producing the ETAs and routing our drivers, and that's already saving huge amounts of money that can be invested in other places. And this is just like a very concrete example, but we're a very mature organization, data science within Bolt, which is already like a mature company, it's not a startup anymore, and it's been helping a lot strategically grow the company. And indeed, we're very close partners to our product organization that is guiding the high level directions where the company is going, of the features the company is working on. And we're close partners. We're helping up to the point where we're actively proposing what to work on, and we're like in a very good collaboration pattern with the stakeholders. They're looking up to our answers. Of course, they've got the best business insight, but we've built quite a lot of business understanding. We've proven impact in quite a lot of impact with our approaches in the past. And we're in a point where we're driving even strategically, I would say, the company with this sort of approaches.
Cool, thank you. Okay, I guess I'm all out of questions. So at the end of this episode, if someone wants to speak with you or contact you, do you have any public place where they can contact you, like Twitter or whatever, if they can? If not, then it's fine.
Facebook, LinkedIn, I'm available, and also by email, which is just my first name, last name at bolt.eu, Andrei.Ilie.
Yeah, I'm also on LinkedIn, not on Twitter.
Okay, cool. Thank you very much. We're at the end of the episode. Thanks quite a lot. We learned new stuff, and I was really curious to know about a lot of stuff. We're not going to hold you anymore in this episode. Thank you very much. Have a great day out there at Bolt, and talk to you possibly soon, or whenever we can meet each other later on. So have a good day.
Yep. Thanks a lot for having us.
Thank you. Bye-bye.
Thanks a lot.
Bye.